good afternoon for most of you, because we are in the time zone where most of the people are from the, let's say, Central Europe or Central East Europe. It is my great pleasure to be the first host of the first seminar in this SEENET-MTP online seminar. I would like just to say a few words about the background. Southeast European Network in Theoretical Mathematical Physics was launched in 2003 under support and initiated by Professor Julius Vess. The network covered 11 Balkan countries and Ukraine and has about 450 members all over the world. Today, we have a great pleasure to have Professor Jonathan Richard Ellis, known more as John Ellis, briefly. I think that, John, you were in Serbia, in Brnjačka Banja in 2003 on the 5th Balkan Congress, if I remember well, with Petar Adžić. And I think you were also now establishing workshop, which was in August 2003. The idea for the online seminar, of course, is based on the pandemic we have been faced for practically 2 years. And the idea was launched by our former student and now staff member of CERN, Marko Simonovic, which was widely accepted, supported also by the Scientific Advisory Committee of our network. And it's a great honor. And I would say that all we are, and me personally, are very indebted to John that accepted to be the first lecturer. Just a few words about John Ellis. Many of you know him and maybe even better than me, but I will try to say in a few sentences about the huge contribution that John gives to physics and to the physics community. So John Ellis is a British theoretical physics, currently Clerk Maxwell Professor of Theoretical Physics at King's College in London, long-time member of CERN staff with many duties and positions in CERN. So John's research is based on phenomenological aspects of particle physics with a lot of contributions, important contributions to many other fields, with an accent of astrophysics, cosmology, and quantum gravity, let's say. John was awarded for his contribution in many cases. I would just mention Mayhew Prize, Maxwell Medal and Prize, Paul Dirac Medal and Prize. He's honored to be the Commander of Order of the British Empire. He's honorary or regular member of many academies and societies in the world, as well as honorary doctor and professor at several universities. He's one of the most cited theoretical physicists in the world. What I would like to underline that John is known for his efforts to involve non-European nations in CERN scientific activities all over the world. Also, we are very much indebted to him for support to the Balkan countries, for my country, for Serbia, for great work for promotion of physics all over the world. Now, John is one of the leader of a very interesting project, a mission that hopefully will be effective in a few decades. And because I'm one of the member with a very small, but still some kind of contribution and membership of that, I'm impressed by his effort to support something on such a long range, which will be covered by many decades in advance. So I'm sorry, maybe I was too long. John, I would ask you to present your talk of using, let me try to say it correctly, searching for ultralight, dark matter, and gravitational waves with the atom interferometers. John, it's your floor.
Okay, well, thanks very much.
So I would ask you to mute To be muted all. Sorry, Milan, can we mute all, everybody?
Okay, can you hear me?
Yes, now it's fine. I hope there will be no interruption more.
Well, you know, it's always nice to listen to some Balkan music, but maybe we could listen to it later. So anyway, thanks for the invitation. I'm glad if I'm considered in some sense as being sort of an honorary Balkan. Anyway, yeah, so I'm going to talk about looking for ultralight, dark matter, and gravitational waves with a novel technology. So after just briefly recapping on dark matter and gravitational waves, I'll discuss this technology that we're proposing to use, and in particular a project called AION, which we're starting to construct in the UK, and I'll also mention some other projects around the world with similar ideas. Now, I'll give some instance of the sorts of physics that one can do in terms of the search for ultralight dark matter, also opportunities in measuring gravitational waves. And I will also discuss this idea that we have for eventually taking this atom interferometry technique into space, as Goran suggested. So I don't really think that I need to spend much time introducing dark matter to this audience. So I think everybody knows that we actually understand only about 4 or 5% of the matter in the universe, which is described by the standard model. The remaining 95% or so is dark stuff. Most of it is dark energy, some of it is dark matter. And the search for dark matter is certainly very high on the agenda of particle physicists. Of course, we would also like to understand better dark energy. Anyway, in my talk, I'll say a little bit later on about the search for dark matter, not so much about the search for dark energy. So, as I think also you're well aware, there's basically two sort of main categories of dark matter candidate that people talk about. So on the one hand, you have ultralight dark matter, so the archetypal example being the QCD axion, but you know, there's many other light bosonic particles that could provide the dark matter via coherent waves coming from FX early in the history of the universe. So, you know, ultralight dark matter is, you know, one of the favored candidates for the cold dark matter. Another possibility is some sort of massive dark matter particle, typically a fermion, a so-called weakly interacting massive particle. So these are kind of the two extremes, a massive fermion and an ultralight boson that forms coherent waves. So in this talk later on, I'm going to be discussing the possibilities of looking for these ultralight dark matter candidates through atom interferometers. Likewise, I don't think I really need to spend much time introducing gravitational waves, which of course were proposed by Einstein in 1916, shortly after he proposed the theory of general relativity. What's perhaps not quite so well known is that in 1936, he actually tried to withdraw the prediction of gravitational waves. And he sent a paper off to the journal, and the journal sent it to a referee. And that deeply incensed Einstein. How dare you send my paper of Einstein to a referee? But the referee commented that actually he thought that Professor Einstein had maybe made a mistake, and that actually his original prediction of gravitational waves was correct. So anyway, Einstein revised his paper, and he predicted gravitational waves again in 1936. So the first indirect detection of gravitational waves came, of course, from observations of the binary pulsar that was discovered in 1974 by Hulse and Taylor. And by now, the change in its orbit has been measured for decades. It's in perfect agreement with general relativity, and in particular, the calculation of the emission of gravitational waves. And this got the Nobel Prize for Hulse and Taylor in 1993. And other binary pulsars have also been measured, and by now there's many very powerful indirect tests of Einstein's predictions. So that was indirect evidence for gravitational waves. How about looking directly for gravitational waves? So as you all know, laser interferometers such as LIGO and Virgo discovered gravitational waves directly for the first time in 2016. They observed a relatively limited range of frequency between, let's say, 100 and well, around 100. A frequency of around 100 hertz. Now, those are great for observing mergers of black holes, mergers of black holes with neutron stars and so on. But there are expected to be many other sources of gravitational waves in different ranges of the frequency. So, for example, quantum fluctuations in the early universe, which can be observed through the cosmic microwave background radiation, in particular its polarization, those would produce observable, actually, quantum gravitational waves with a frequency of 10 to the minus 16 hertz or so. And then there's pulsar timing arrays, which I'll come back to later on, which are most sensitive to waves with a frequency around 10 to the minus 8 hertz. And I'll come back to them as well. So the project that I'm involved with, called AION, and eventually its successor spatial project AEDGE, would be in a range of frequencies, which is sort of often called the mid-frequency range, or the range around 1 hertz, intermediate between the terrestrial laser interferometers like LIGO and Virgo and space laser interferometers such as LISA. And I'll be discussing later on the scientific interest of looking in that particular frequency range. So here's a reminder of the observations by LIGO and Virgo. So in blue, you have the black holes that they've observed. In purple, the black holes whose existence has been inferred from electromagnetic observations. Down the bottom in yellow, you have the masses of neutron stars inferred from electromagnetic observations. And then you see, indicated by these sort of merging arrows here, the mergers that have been observed of neutron stars with black holes with black holes. And perhaps among the most interesting ones, which I'm going to come back to later on, are these high mass black holes, which are interesting from the point of view, perhaps, of the formation of the supermassive black holes that are known to exist in the centers of massive galaxies. And I'll come back to that later on. So LIGO and Virgo, and now also CAGRA, are having a great time observing these stellar mass black holes. The LISA project for a laser interferometer in space is aimed at a different frequency range, around 10 to the minus 2 hertz. And it's in particular interested in phenomena involving types of supermassive black holes that exist in the centers of many massive galaxies. I might mention there's also a couple of Chinese projects, Taiji and Tianqin, which are also aimed at a similar scientific objective, a similar frequency range. Okay, so if we look here at the detectors operating in different frequency ranges, as I already mentioned, we've got LIGO and colleagues around 100 hertz, LISA and colleagues around 10 to the minus 2 hertz, and the pulsar timing arrays around 10 to the minus 8 hertz. So what you see here is that there's actually a gap between the ground-based laser interferometers and the space-borne laser interferometers. And that's a gap which we are interested in filling with atom interferometers, as I'll be discussing later on. There's, of course, also a gap between the pulsar timing arrays and LISA, and maybe I'll say a few words about that later on. Okay, now I've been mentioning this project AION and related projects which plan to use atom interferometers. And these projects piggyback on global interest in deploying quantum science and technology. And this chart here shows you that in 2020 already, the world was piling an enormous amount of money, more than $20 billion is the estimate, into quantum science and technology. And some of that money was going into quantum sensors, and some of those quantum sensors have applications to pure science, which is, of course, the field I'm going to be interested in. But they have many other applications, and I think there's actually an opportunity for us fundamental physicists to cooperate with scientists in other areas and maybe do developments in common. Anyway, we're in Europe, and so here in red, I've outlined the resources going into quantum science and technology in Europe, and in particular, I highlight what's going on in the United Kingdom. So, in addition to other applications of quantum technology, the UK government recently assigned a significant pot of money to quantum sensors for fundamental physics program. And the initial funding covers 7 projects deploying quantum sensors, for example, atomic clocks, quantum simulators of black hole physics, and so on. And among these 7 samurai is the project that I'm involved with called AION. So in the top left here, I show the collaborators on AION. I've highlighted in red the collaborators for my institution, King's College London. I've highlighted in green the graduate student who does all the work. So there's a total of 7 universities and the UK National Lab who are involved in the AION project. And I should say that we collaborate very closely with a sister project in the US called MAGIS. And in fact, some members of AION are also members of the MAGIS collaboration, which is constructing an atom interferometer at Fermilab. So what's the basic principle of an atom interferometer? So we're all familiar with a light interferometer. So you start off with a laser beam, you split it into 2 sub-beams which follow different paths. Then you bring them together again, and you look into interference patterns, like these light fringes, which are illustrated up here. And everybody knows that LIGO and Virgo observe shifts in these interference patterns, which occur when a gravitational wave passes by. So what do you do with what is an atom interferometer? So you have an atom cloud, you fire a laser at it, which splits the atoms into excited states, leaving some as ground states. Then you hit them again with a laser, and some of the excited states go back to ground states. And in this way, you can construct interference between atoms that have followed different paths. Here I just illustrate a case where you just have 2 transitions, but you can also consider much more complicated patterns where there's many transitions between ground state and excited state. Each one of those involves some transfer of momentum between the laser beam and the atom. Transfer of momentum means you're following a different path, and then you look at the interferences between the atoms following those different paths. You look at these atom fringes, which are illustrated in the bottom right-hand corner here. Okay, so AION is actually a staged program with 4 stages, which I will try to take you through. So the first stage is to build a 10-meter device, which, as I'll explain, is going to be located in the Oxford Physics Department. And we're also doing some preliminary investigations for a possible follow-on 100-meter device, which, as I will describe, could possibly be located at CERN. After the 100-meter device, the largest reasonable terrestrial device that one could build is 1 kilometer plus or minus. So that would be stage 3. If you want to go beyond that, then you need to go into space. And that's the AEDGE project, which I will discuss later on. So anyway, let me start off with the relatively modest first stage. So as I said, this is to be located in the Oxford Physics Department, which has a beautiful seismically stable basement. But I should perhaps mention that these atom interferometers, you look at interference patterns between clouds of atoms, which are basically thrown up vertically and then interrogated or excited by the laser beam, which is also vertical. So you need a 10-meter vertical space, and that you have in the Oxford Physics Department. There's, in addition to the vertical stairwell, there's also a dedicated laser laboratory. This is, from the point of view of infrastructure, a perfect place to build this 10-meter device. So towards the end of last year, we had a collaboration meeting at Oxford, and some of us actually assembled in the basement where AION 10 is going to be located. So here we all are wearing our masks. Here I am wearing my mask over here. And somewhere here there should, yes, here this is Oliver Buchmüller, who is the spokesperson of the AION project. So, so far, we're not actually constructing anything on that particular site, but there's a lot of work in the laboratories in the different universities, building up their equipment and doing some preliminary studies for the atom sources. So here's some pictures from some of the participating universities. So as I mentioned, we use lasers to to split atom beams, and the split beams follow different paths. The splitting between the paths increases with the number of momentum transfers, MTs, that you can kick them with the lasers. And eventually, we want to go up to not just hundreds, thousands, maybe even tens of thousands of these laser-induced transitions and momentum transfers. In order to do that, you need a very stable laser system. And this is one of the things that my collaborators have been working on. This is an illustration of one of the laser systems. And they've been able to stabilize the lasers to an extremely high precision. A high precision, which is way beyond what we need for our science objectives. So, you know, we've got a whole list of technical objectives that will make our experiment possible, but at least one of the boxes has now been ticked. Okay, so as I said, the 10-meter device would be located in the Oxford Physics Department. And there are various sites that we're considering for the possible location of the 100-meter device. So there's a couple of sites in the UK. There's a mine in a place called Bulby, and there's a national laboratory at Daresbury in the UK, which are possible sites. But we've also been talking to CERN engineers about possibly locating AION 100 in one of the access shafts for the LHC. So there's this shaft here, which is 140 meters tall. And we're working to understand the seismological background there, temperature variations, radiation protection, electromagnetic interference, and so on. And so these are early days yet, but at the moment, it seems that this would be a very good site for AION 100. Now, as I mentioned, there are other atom interferometers projects underway. I already mentioned the MAGIS project in the US. In France, there's a project called MIGA, which is under construction in a former nuclear bunker. So here you can see the guy with his finger on the button. Fortunately, he's not there anymore. And instead, the site has been turned over for doing fundamental physics experiments. Looking to the future, if CERN ever builds the Future Circular Collider, FCC, then there is foreseen a 500-meter vertical shaft, which would also be very good for putting an atom interferometer. Turns out that you can access it by road at the top. At the bottom, sorry, I jumped the gun. So the FCC has a 500-meter vertical shaft. There is this other possible site in Switzerland, which is the Gotthard base tunnel. So this is a railway line, and there's an access shaft of 800 meters, which would also be perfect for our purposes because you can access it by road at the top and by train at the bottom. So we're thinking about possible sites for future AION stages. Now, as I mentioned, and as Goran also mentioned in his introduction, we're also interested eventually in going into space. And that's a project which we call AEDGE, Atom Experiment for Dark Matter and Gravity Exploration. And we submitted an expression of interest for this project to the European Space Agency. They did a call a couple of years back for projects to be considered for their science program in the period around 2050. So the principle of this experiment is very similar to what I've been discussing for AION. Of course, you don't have to worry about making it vertical because you've got a device with 2 satellites in medium Earth orbit, which are in free fall. And the clouds are located in or near the 2 satellites, and you have a laser system which interrogates and excites the 2 atom clouds. So the European Space Agency commissioned a senior scientific committee to review various expressions of interest. And they suggested 3 science areas for possible future large missions, one of which was new physical probes of the early universe, which might include AEDGE. And they also suggested possible medium-scale missions, in particular missions using possibly cold atoms to probe quantum mechanics and general relativity. So we've been engaged in bringing together the European cold atom community to present a unified roadmap for such possible missions to the European Space Agency. And tomorrow we hope to get a white paper on the archive. And I see that Goran and Milan, probably other people on this video conference, are co-signatories of this proposal. So we prepared this with a community workshop, which took place last September. And as I said, the white paper, which we're producing as a result of that, should be out tomorrow. Okay, so I talked a lot about projects and technology and so on and so forth. Now, let's discuss the science. So I'll start off with ultralight dark matter. So I showed you this slide previously. So atom interferometers are particularly good at looking for coherent waves of ultralight bosonic dark matter, as I'll now discuss. So what we're thinking about primarily is some dark matter field phi, which might be coupled to the photon, coupling called DE, might also call it coupled to gluons and W bosons, but we focus on the photon, and which might also couple to matter fermions, in particular the electron. So these two pictures here indicate the sensitivity of this type of atom interferometer to the photon coupling on the left and the electron coupling on the right. So of course, there's been a bunch of experiments in the past, ongoing experiments, and they exclude large values for these couplings, as shown by the shading in these two pictures here. So what I also show here are the prospective sensitivities of AION 10, AION 100, AION 1 kilometer, and AEDGE. So in particular, I highlight here AION 100. I just wanted to illustrate the fact that these AION experiments have the capability of giving sensitivities orders of magnitude better than the current sensitivities. And in fact, even AION 10 has a decent chance of making some inroad for a range of dark matter particle masses around 10 to the minus 13 electron volts. So this may not look very impressive on this plot, but just look at the scale. This will be something like an order of magnitude more precise than the current experimental limits. So what I showed you on that slide was the sensitivity to dark matter fields that couple linearly to the photon or to the electron. You can also consider quadratic couplings of the bosonic field, which are illustrated over here. And here we show the prospective sensitivities of AION stages and also EDGE to this quadratic coupling of ultralight dark matter to ordinary matter. And here again, you see that there's a capability of exploring couplings which are orders of magnitude smaller than the current sensitivities. Okay, so moving on from ultralight dark matter, now let me come to back to gravitational waves, and in particular to this gap between the sensitivities of terrestrial laser interferometers and space laser interferometers. So in between, on the right, LIGO, Virgo, Cagra, and on the left, LISA. So as I will illustrate, here there's plenty of interesting scientific issues in astrophysics, in cosmology, and in fundamental physics, looking at the formation of supermassive black holes, for example, looking for a stochastic background of gravitational waves coming from an electroweak phase transition or from cosmic strings, etc., etc. So let me start off with black hole mergers. So here I've taken the example of AION 100. These contours correspond to a signal-to-noise ratio. And what you see here is that the 100-meter device would already be sensitive to mergers of black holes weighing 10 to the 3, 10 to the 4, or even more solar masses. They're sensitive to higher masses than LIGO Virgo just because these laser interferometers work at lower frequencies. So that was one example of black hole physics that you could do with a 100-meter device. Here's an example with what you could do looking for a stochastic background of gravitational waves due to a first-order cosmological phase transition. And what's interesting here is that you could be sensitive to phase transitions involving a U1 gauge boson weighing 100 TeV, much heavier than what you could access directly in a collider experiment. Now, of course, as I've emphasized previously, AION is not the only atom interferometer experiment looking for this sort of physics. And I got here one plot from the MEGA proposal showing how they would also be sensitive in a range of frequencies around 1 Hertz. Okay, now what is actually the astrophysical interest in looking at these intermediate mass black holes with masses between, let's say, 100 solar masses and the million solar mass black holes that you have in the centers of galaxies? Well, of course, the big question is, how did those supermassive black holes form? And there's various different ideas for how that might have happened, which are illustrated in this picture here. So, for example, maybe what happened was that the first generation stars, population 3 stars, very massive stars, collapsed very quickly to make black holes weighing maybe 100, maybe 1,000 solar masses. And then maybe you had a hierarchical set of mergers which gradually built up intermediate mass black holes, heavier black holes, and eventually supermassive black holes. Or maybe you formed in the early universe protogalaxies. And maybe when those protogalaxies were formed, already in the center of the protogalaxy, you had an intermediate mass black hole, maybe 10 to the 4, maybe 10 to the 5 solar masses, which then subsequently merged to form the supermassive black holes. Now, in either of these scenarios, you might expect that there will be some leftover intermediate mass black holes with masses between, let's say, 100 and 100,000 solar masses. And it would be interesting to study the population of such objects through the gravitational waves emitted by their mergers. So that's what's illustrated here, where I show you the sensitivities of LIGO, AION and EDGE, and LISA to gravitational waves over a large range of frequencies, going down to 10 to the -6 Hertz and up to 10 to the +4 Hertz. And here you have the mid-frequency band in between LIGO and LISA, which is the band in which atom interferometers would have the greatest sensitivity. So LIGO, of course, observes the mergers of black holes weighing a few dozen solar masses. And LISA would be great for measuring the mergers of black holes weighing millions of solar masses. But if you want to observe intermediate mass black hole mergers, you want to observe in the mid-frequency band, and that's where AION and EDGE come to the fore. Now, what's interesting is that the observations of AION and EDGE would actually be sort of complementary to what you could observe with LISA or with LIGO. So, for example, LISA might see the early stages of an intermediate mass black hole merger, but then the actual merger itself would show up in AION. Or AION might observe early stages of the mergers of LIGO-type black holes, and then the actual merger itself would subsequently be observed by LIGO. And one can show that, for example, with AION or EDGE, you could predict in advance the time, the redshift, the direction, and the mass of a black hole merger, which would subsequently be observed by LIGO-Virgo. So here I've compiled the sensitivity as a function of redshift to mergers of black holes weighing between 1 and 100 million solar masses. So LISA, of course, is great for measuring the mergers of supermassive black holes, and LIGO is already established that you can measure the mergers of black holes weighing a few tens of solar masses. But there's a gap in between, and that gap in between is the one that you would fill with AION and eventually EDGE. So I've highlighted here the fact that these detectors are complementary because often you can measure different stages of a merger in different detectors. So early stages in one detector and the late stages of merger in a different detector. I've also highlighted the existence that's predicted in standard solar models of a mass gap, somewhere around 100, 150 solar masses. You do not expect to see astrophysical black holes. But if you did see them, that might be indicative of new physics beyond the standard model. And AION and LIGO are in principle sensitive to such things. AION out to larger redshifts than LIGO. So this is a similar plot showing the sensitivities to intermediate mass black hole mergers for AION, which again, as you see, is complementary to LISA and the future terrestrial gravitational wave detector, the Einstein telescope. What's interesting here is that these detectors should be sensitive out to redshifts of 100 or even 1,000. So really back in the very early universe, so far back that maybe the constituent black holes would not be astrophysical in origin, but might be primordial black holes. And this right-hand plot shows that you could also observe mergers of black holes with neutron stars, again, out to large redshifts of the order of 10. Okay, so that was astrophysics. So how about fundamental physics? So one of the things that you can do is use these measurements to constrain the graviton mass. So LIGO and Virgo have already done this. They constrain the graviton mass to be smaller than about 1 or 2 times 10 to the minus 23 electron volts. Now, an atom interferometer in the future could do a lot better for 2 reasons. One is because it observes over a longer period of time, so you get greater precision. And another is because you observe the mergers of heavier black holes, which have lower frequencies, and lower frequency black holes are more sensitive to a possible mass for the graviton. So this is something that I studied with Ville Vaskanen. We showed that AION 1 kilometer observing a LIGO-Virgo-like event would be sensitive to graviton mass of 10 to the minus 24 electron volts. If we can see mergers of heavier black holes, you'd be sensitive to somewhere around 10 to the minus 25 electron volts. And if you could observe with AEDGE mergers of black holes with a total mass of 10,000 solar masses, you'd be sensitive to a graviton mass of 10 to the minus 26 electron volts. So 3 orders of magnitude improvement over the current experimental upper limit. So I've done astrophysics, I've done fundamental physics. Now I want to do early universe cosmology. So in many extensions of the standard model, you have in the early universe first order phase transitions. Those first order phase transitions produce bubbles, the bubbles collide, and those bubble collisions generate gravitational waves. In fact, it's slightly more complicated than what I just said. In addition to bubble collisions, you can also get gravitational waves from turbulence and sound waves in the plasma following the transition. So we looked at a couple of models. One is the standard model with an additional dimension 6 Higgs interaction. And the other one is adding in an additional U1 Z prime boson. And it's interesting to contrast the sensitivity that you get from colliders with the sensitivity that you get from these cosmological studies of gravitational waves using atom interferometers. So here's an example of a gravitational wave signal that we expect coming from a U1 phase transition. So the total signal is shown here as a solid line. It has components coming from bubble collision, sound waves, and turbulence. So we chose here a Z prime weighing 100 TeV, so beyond the reach of colliders, with a coupling which is sort of plausible in the framework of unified theories. And you see that it would produce a stochastic background of gravitational waves, which might be observed with LISA or with EDGE or with AION 1 kilometer. And this is a more general survey of the sensitivities to such a U1Z prime model, LISA, AION 100, AION 1 kilometer, and EDGE. And you can see that AION 100 project, which will come in a few years before LISA, already starts to have interesting sensitivity, and the best overall sensitivity would be provided eventually by EDGE. Okay, so now let me discuss another topic where you can look for a stochastic background of gravitational waves, which will be sensitive to another type of fundamental physics. I'll be spending a bit of time now discussing pulsar timing arrays. So pulsars are, of course, very precise clocks. They send out signals like lighthouses, but if you have a gravitational wave goes by, the timing of those signals can be distorted. And various collaborations around the world have been looking for such distortions of the pulsar timing. And in particular, a bit over a year ago, the Nanograv collaboration reported results from observing 47 pulsars over 12.5 years. And the data are shown here. So at frequencies above 10 to the minus 8 hertz, it just looks like noise. But below 10 to the minus 8 hertz, it looks like there is a signal. And in the jargon of the pulsar timing array business, they say there is strong evidence for a stochastic common spectrum process at frequencies less than 10 to the minus 8 hertz. So here on the right, there is a plot of a fit. Gamma is a spectral index. A is the overall amplitude. And you see here that they results could be fit by an effect with an amplitude of about 10 to the minus 15 and a slope which is about 5. Now, one of the reasons why these pulsar timing arrays were put together was to look for gravitational waves emitted by pairs of supermassive black holes. Now, they would give you a signal with a spectral slope of 4 1/3. So this vertical dashed line here, which is consistent with the Nanograv data, although Nanograv might prefer a slightly steeper slope. It's worth saying that astrophysicists might have a problem getting a large enough amplitude A. And there's specifically a remark in the Nanograv paper saying the amplitude may imply the black hole mass function is underestimated by the astrophysicists, specifically when extrapolated from observations of the local supermassive black hole population. So there may be more supermassive black holes out there, and maybe they would be needed if you wanted to understand the Nanograv data. However, it's not yet been established that the Nanograv signal is actually due to gravitational waves. If it was, then there would be a characteristic angular distribution. If you look at the correlation between pulsars at different angles, which was calculated by Hellings and Downs. Unfortunately, Hellings just died a few days ago. So far, there's no indication that there is this Hellings-Downs effect. The data are compatible also with an isotropic distribution. Okay, so where does the fundamental physics come in? So if you have cosmic strings, they sort of wave around in the early universe, and they form loops, and those loops collapse by the emission of gravitational waves, and that gravitational wave emission could be the origin of the nanograv effect. So the background here is a simulation of cosmic string network by the Cambridge Cosmology Group. So together with Marek Levitsky, what we did was we calculated the effective spectral index and amplitude that you would get as a function of the tension in the cosmic strings. So it turns out that there is a tight correlation between the amplitude and the spectral index, which is shown here. And as you move along this line here, then that corresponds to varying the strength of the cosmic string tension. And this is a characteristic, this rainbow curve is a characteristic signal of cosmic strings. So nanograv favors this range here, and that's indicated by this range of cosmic string tensions between 10 to the minus 10 and 10 to the minus 11. So we don't know whether nanograv saw gravitational waves or something else. If they were gravitational waves, they might be astrophysical in origin, but they might be cosmic strings. If they are cosmic strings, then you would expect that spectrum to continue almost flat up to relatively high frequencies. The amplitude would be below the sensitivity of LIGO, but it would be within the sensitivity range of AION and AEDGE and also LISA. And it would be interesting to look carefully at the spectrum, because it could tell you about processes that occurred in the very early universe. So this nearly flat curve corresponds to a conventional adiabatic expansion. But if you have an earlier period of matter dominance or an earlier period of kination, then you get a deviation from this smooth, nearly flat curve. And by measuring this curve, you could tell what happened to the expansion of the universe in the very early stages. Now, I've talked about 10 to the minus 11, which is close to the current upper limit on the cosmic string tension. What is the minimum value of the cosmic string tension that AION, LISA, and AEDGE could be sensitive to? And the answer is somewhere around 10 to the minus 18, which is over 3 orders of magnitude smaller than the tension, the upper limit on the string tension set by LIGO. And well, AION 1 kilometer could be in operation by the year 2030, ahead of LISA and ET. So there's many other topics beyond ultralight, dark matter, and gravitational waves that one can do with cold atoms in space. You can probe the gravitational redshift, probe Bell inequalities, the equivalence principle, variations in the fundamental constants, dark energy, etc., and, for example, Lorentz violation. And this is something which I also looked at together with Ville Vaskinen. So here we have a possible parameterization of Lorentz violation in the propagation of gravitational waves. LIGO has set upper limits, which are relatively sensitive if this parameter alpha here is bigger than 2. But if the parameter alpha is smaller than 2, then the most sensitive measurements are those at lower frequencies, and that's where AION and EDGE come into play, and they could set limits or make measurements which are 10 to 1,000 times more sensitive than LIGO. Okay, so that brings me to the end of what I wanted to say. Experience with electromagnetic waves shows that the great advantage is making astronomical observations over a range of different frequencies, and the same is expected to be true in the era of gravitational astronomy. There's many opportunities to search for new fundamental physics and also, of course, astrophysics. And I highlighted the hint of cosmic strings from the nanograph pulsar timing array, which is possibly due to fundamental physics in the early universe. So AION and EDGE offer a program for exploring, in particular, deciHz gravitational waves using atom interferometry. I've discussed some of the opportunities in fundamental physics, astrophysics, and cosmology, but there's many more that haven't yet been explored in detail. So, thank you very much.
Thank you, John. Thank you very much for a very informative, very nice review. I think now we can come to the questions. I suggest two ways to do it, to raise a hand or to send a question to chat. It's up to you to decide. Let me see if I can see.
Goran, may I ask a question?
Of course, please, Peter.
John, you mentioned ultralight, dark matter, and its a sensitivity. You didn't mention perhaps some background events that you could look at. And the second question, quick, how this would proceed with dark energy? You mentioned that, but how this would help that we also detect some dark energy?
Sorry.
Did you hear my question?
Yeah, I heard your question. I have had a little bit of trouble here trying to see what window I'm broadcasting. What window are you seeing?
Mm-hmm.
At the moment, nothing. At least me.
Nothing. Okay.
Yeah, you should start to share your screen.
Yeah.
Or try it again.
Sorry,
Okay, I see you now.
I got a call which completely messed up my screen. Wait a second. So now hopefully you're seeing
Yeah.
my screen. Okay, I'll just blow this up a little bit. Okay, sorry. So could you please repeat the question? I was focusing on this.
Okay, the question was the dark energy. Okay, just first dark energy. Okay,
so dark energy, there are many models in which dark energy is due to some sort of field, an ultralight bosonic scalar field of the type that I was discussing. So that there is some sort of a mapping from the sensitivity of AION and EDGE onto the parameter space of dark energy models. So I'm not an expert on that. Some of my collaborators are more expert than I am, but that's the connection.
And just one more comment, rather administrative. Does AION collaboration have any relation with newly raised and newly founded collaboration quantum forum at CERN, quantum technology? I understand that AION is focused only on UK. Am I right?
So the funding that we have at the moment comes from the UK, but there are various people who have been working in the UK who remain affiliated with AION. In Spain and Poland in particular. So I think that for the next stage in AION, we would be very much interested in talking to potential international partners. And in particular, if we cite AION 100 at CERN, I think this would be the obvious direction to go.
Okay, thanks.
You're welcome.
I think there was also a question about the ultralight dark matter, but Peter, did you want to precise the question?
Yeah, I just wanted to speak on sensitivity because I didn't hear that John mentioned background. What are the events that could cause some background events and some difficulties in sensitivity? We know for gravitational waves, which had to cope with LIGO and Virgo, but what about ultralight dark matter?
So I think so there are seismological effects, so-called gravity gradient noise, which can be important depending on the sensitivity which you're trying to reach. Unfortunately, I don't have a picture of this in this particular stack of slides. So the MAGIS people have measured it at the Fermilab site, and they think that this gravity gradient noise is manageable. Now, we've got some collaboration from engineers at CERN to measure the gravity gradient noise, the seismological noise here at CERN. And the first indications are that the noise level is similar to Fermilab, which would not create a problem for the sorts of measurements that we want to make. In fact, as we speak, they're conducting more detailed measurements, specifically at the top and bottom of this access shaft that we would like to use.
Okay, I see it's a possibility for our colleague Sasha Topic to put a question.
Hello, John. It's a great thing to have you here and an honor. I don't have a question as such. I only have a comment and an addition. Our Institute of Physics about 2 years ago has become a member of global collaboration that aims to search for ultralight dark matter. It's called the GNOME network, and basically it functions as a global GPS network of magnetometers that can detect the passage of the Earth through the topological defects or some kind of clumps or the axion stars. And we just published as a collaboration a paper in Nature Physics. So I think it's important to just say this because it is the community that's very closely related to our institute. So, and thank you once again for this lecture.
Well, thank you for telling me about your recent publication. Maybe you could send me a link to it so that I can have a look at it.
Yes.
So I think we would be very interested in building up good relations with all the other groups interested in ultralight dark matter and maybe collaborating in the future.
Okay, thank you. Further questions? I have one. John, what about the primordial gravitational waves correlated to inflation due to it's a very long wavelength and very low frequency, reasonable strain? Do you think, and what you think about the possibility for direct or likely indirect detection of these effects?
Yeah, so let me see, where did I go? Yeah, so the range of frequencies which you're sensitive to with a cosmic microwave background radiation, they're very low, of course, as you know, 10⁻⁻16 or so. And we know that the scalar perturbations at that sort of frequency have an almost flat spectrum. Now, of course, we don't know whether there is a tensor spectrum, a gravitational spectrum. And R40, we don't know whether it's scale invariant like the scalars almost are or not. But I think it's fair to say that for there to be a primordial tensor spectrum related to what we've observed with the cosmic microwave background, there would have to be a strong violation of scale invariance. It's not impossible. There certainly are models in which that happens. Another possibility is that there might be some feature in the inflationary expansion or whatever other dynamics is responsible for primordial tensor perturbations. And I'm sorry that I don't find it here. Again, it's not in this stack. But in a paper that we put out last year, we discussed the sensitivity of AION and AEDGE to primordial black holes as might be produced if there was a feature in this primordial tensor spectrum. And you'd be sensitive at a level far below the size of features in the spectrum that would give you primordial black holes that could explain the dark matter.
Okay. I see colleague Vasilis Panos, please.
Hi, John. Thanks for the nice talk. Yeah, actually, my question, it was about Gora question, but I do have one more. When you discuss about this ultralight dark matter, you don't worry about the Lyman alpha bound? I mean, this is my worry.
Lyman alpha bound.
Yeah, the structure, all this structure formation bounds. The same for which, let me say,
Okay.
more or less neutrino is excluded as a dark matter candidate, right?
Right. So let me just find this. Yeah. So there is a lower limit on the bosonic dark matter mass, which is around 10 to the minus 21, 10 to the minus 22. From there's a whole bunch of constraints on structures which constrain so-called fuzzy dark matter. So that would be in this range over here, which we didn't include in our plot. So this range of ultralight boson masses that we're talking about, as far as I know, is completely compatible with all the astrophysical constraints.
Okay, thanks. Okay, thanks a lot.
I think there is something from Zagoria. Maybe Neven. Please, Neven.
Okay, thank you. John, you mentioned lots of possibilities to probe fundamental physics. Can AIONs look for extra dimensions, for example?
Offhand, I don't know how you would look for extra dimensions.
Yeah, I guess the spectrum of gravitational waves should somehow depend on extra dimensions. Maybe there is a possibility also to look for that.
So one thought that occurs to me off the top of my head is if you had some dimensional transition in the early universe, this might cause a period of non-adiabatic expansion. And this is something that you might be sensitive to. But to tell you the truth, I haven't thought about extra dimensions in any detail.
Okay, thank you.
A good point for further thinking. Okay, let me see. Okay, I see in the chat, maybe, I don't know, it's to it's to everyone. John, maybe you can have a look to the chat, or you want me to read it?
I'm looking at it. This is from Glauber.
Yeah, exactly.
So could you comment a bit on the difficulties that we need to be overcome for putting these atoms in free fall? So obviously, the sort of terrestrial experiment that we're talking about requires a good vacuum. It doesn't have to be fantastically good, but no, a decent vacuum. No, you'd have to make a vacuum tube which is 10 meters, 100 meters, 1 kilometer long. But in principle, this is not a problem, right? I mean, it's the engineers build vacuum tubes which are 27 kilometers long. So I don't think that's a particular difficulty. One of the things perhaps I might mention is, so AION and MAGIS plan to use vertical shafts. The MEGA experiment in France that I also mentioned has a different geometry where they have a horizontal shaft. And that then gives you an issue because you won't be in free fall for very long. Right? You've got a horizontal tube. You put an atom cloud into this tube, but it doesn't stay in the tube very long. So I think if you want to get a long period of free fall, being in a vertical tube is the best option. Does that answer your question, Glauber?
Hi, John. Maybe it's easier if I use the microphone. I was actually wondering more about the mutual interactions between the atoms in this atomic cloud. I mean, like Van der Waals type of interactions. Is it not a problem?
So, sorry, interactions between the atoms and the cloud?
Yes.
Yeah, no, this is not a problem. So I might also mention something else which is not a problem, which is when we're thinking about the space experiment. So in fact, Peter Graham and collaborators suggested the possibility of not having your atom cloud inside the spacecraft, but actually outside. And when you first hear about this, you think this is completely crazy. But these atoms are only affected by light with a particular frequency. And the sorts of photons that you have dashing around the universe, they have other frequencies. So at least for the durations where you want to have these clouds being interrogated by the lasers, there's no problem with having them outside the spacecraft. And this is an option which in my slides I called AEDGE plus. So here I have AEDGE, and then in outlined dashed I have AEDGE plus. And I didn't comment on this, but AEDGE plus would be potentially interesting, also down to lower frequencies than the optimal frequency for LISA.
Okay.
I have one question more, Goran.
Yes, please.
John, I was wondering, considering the space experiment, is any contact with alpha spectrometer, and some you think that some connection can be done there? Have you considered such possibility?
I don't think so. I think it's a very different sort of experiment.
Well, it will be the same space station, as it probably.
So I think the general feeling among space scientists is that it's better not to mix two different types of on the same satellite.
I see.
Now, of course, the International Space Station is something different. So, there are, in fact, it is, in fact, a cold atom experiment on the space station, which observes Bose-Einstein condensates. And there are ideas for doing future Bose-Einstein condensate experiments on the space station. But I think the sort of experiment that we want to do you want to go to extremely large path lengths. We're thinking typically of 40,000 kilometer path lengths, and that's a lot bigger than the International Space Station.
Okay, thanks.
Okay. Is there any other question? I will give 1 or 2 minutes more for the questions. Just John, sorry, I will announce the next seminar, which should be on 16th of February with Ignatios Antoniadis as a lecturer. And I would like to say that in the organization of that, we are together with Ioannis Rizos, with Maria Dimitrijević-Čirić from Belgrade, and Mirela Babalik from Bucharest, and Milan Milošević from Niš, who is helping us. I would like to thank them, and they will also be the moderator in the future. I see some question. Okay, that's just thankfulness. So the last opportunity, the last call for the next question or more questions. If not, I would like first of all to thank John again for a very nice talk, for a nice review, and I think we will keep in the loop through this seminar or with some other activities we are planning for this year. And also to thank to all the participants, to all people who follow it and put the question which raise the importance and impact